These are the designs and inventions of one man, a man concerned with the overall design of human activity. His is a unique world, one of nuts, bolts, angles, of dreams and practicalities. For over a third of a century, this man, R. Buckminster Fuller, has been challenging, dismaying, and delighting the designers and architects of the world. The public has come to know him through his now familiar geodesic domes. He himself is a prototype, the first of a group of men for the Fuller world, the comprehensive, anticipatory design scientist.
The word design is a very powerful word, very popularly used word. But I think that in recent decades, and certainly even possibly for centuries, the word design has been used in its lesser meaning rather than its more powerful meaning. During the period since World War II, since the era of the jet and then the rocket, the Sunday New York Times runs a series of want ads immediately following the financial news. It's a different position for want ads than the old want ads just for servants and so forth. These want ads immediately following the financial news, right in the financial pages, usually quite large box ads in which you find the largest, most prominent, most powerful corporations advertising for somebody called a designer, a design engineer or design scientist. What's interesting about these ads is they try to sell the company to this proposed design scientist whom they would like to hire. They tell all about the extraordinary scientific challenges which their corporation is undertaking to accept, and they tell all about the thoughtfulness of the corporation towards that design scientist. If he will join up with them, they will take care of him for life. These are really quite extravagant representations in contradistinction to customary want ads. What's most interesting about all of that to me is that there is no category within the technical institutes, Massachusetts Institute of Technology, or within any of the other technical institutes I know of. There is no category in the curricula listed under design science or design engineering. The word design has been added by these companies to the word engineering or scientist. What they want, quite clearly, is a man who has the extraordinarily reliable kind of disciplining that a scientist has had or that an engineer has had, plus a great deal of ingenuity, something innate that could not be taught at a university. And that's the reason that there are no such university or technical institute courses, because you cannot teach invention. You can teach people you can help them to discipline themselves, but discipline in the end is a self-initiated affair. So that it is the initiating, it's the self-starter function which is unique to individuals that cannot be given to the individual by an educational system. And that is what they're looking for, is a man who has this individual quality, plus the great reliability. So in asking for a man who is a design scientist, you're asking for a man who has that great capability and who is able to break through the disciplining of which says do not appraise the significance. A man who breaks through and does appraise the significance and begins to see the interrelated significance of a plurality of specializations, and then begins to integrate those capabilities, integrate those potentials accruing to the new frontier information, and not only integrates the information in the terms of significance of you might be able to now shoot very much further, much faster, much higher, but is able to go further than that and is able to actually what we call reduce to practice, that's the technical term, reduce to practice a concept of potential use. It requires real invention.
Reduced to practice is just what Buckminster Fuller has been doing all his life. He works from his own well-defined principles. One of them, that all the resources of the world must be at the disposal of all mankind. Another, that the best method involves the maximum utility from the minimum amount of materials. This second concept, the word Dymaxion, and Buckminster Fuller came into public view with the Dymaxion House in 1927. The name came from a combination of the words dynamism, maximum, and ions, and it means maximum gain of advantage from minimal energy input. The single-family house, built on the wire-wheel tension principle, was a shock to the public. The upper deck was an open-air relaxation area. The deck below contained all living quarters, 2 bedrooms, 2 bathrooms, a living room, study, and service room. While the single-family house was spectacular, the 10-deck Dymaxion apartment building was revolutionary. It demonstrated completely the Fuller concept of self-sustaining shelter. In the sketches Fuller made to illustrate its flexibility, the 10-deck building was deliverable by Zeppelin. On approaching the site, the dirigible would drop a bomb, blasting a crater for the building. The structure was lowered into the hole, as Fuller said, like planting a tree. It was supported by temporary stays until the cement, poured around the base, hardened. The central mast-like tower contained the mechanics for services like elevators, air conditioning, and waste disposal, energy outlets for cooking and laundry utilities, and bathroom units which could be separately manufactured and flexibly installed. Not only was Fuller designing an extraordinary structure, he was proposing a new industry where the houses would be mass-produced and cost-figured by the pound. At 1927 prices, the 10-floor apartment house would have cost under $25,000, the single-family house $1,500. Translated to 1960, that $1,500 would be $4,800. In a 1927 drawing, Fuller saw Dymaxion housing offering the possibility for true world citizenry. The self-sustaining houses would be provided and delivered anywhere on the globe by a service industry just as telephones are. There were other Dymaxion inventions, the Dymaxion car in 1933. The 11-passenger vehicle was capable of 100-mile-an-hour speeds. Crowds gathered to watch the test runs. Celebrities came, among them Amelia Earhart. Aeronautically streamlined with single rear-wheel steering, the car was extremely maneuverable. Although it was 4 feet longer than the conventional 1933 car, it could park in a shorter curb space by heading in directly, then tailing sideways. It could turn in its own length. Labeled too extreme for mass production 30 years ago, many of its features have been incorporated into contemporary automobiles. Behind the domes, the car, and the houses lies Fuller's ability to see connections between happenings, sciences, needs, and resources. All of them events that fall into the Fuller definition of universe as the aggregate of all men's experience, where no event is lost, but each is available for further development and understanding.
When we use the word design, then, in that sense, we're talking about a very extraordinary kind of an undertaking. And it is something I'm sure that is innate, possibly innate in all human beings. Children show enormous inventive capability, but most of them get frustrated in demonstrating that inventive capability quite early. You see it's still vigorously operative in children when they're doing their first drawings and making their first sometimes sculptures, but primarily drawings, just playing. You see their imagination work in playing. When they construct situations, they build houses. They're able to build a battleship out of a soapbox, and they feel all the different parts of that ship. They've seen pictures of the different parts, and people looking at them don't realize that they're out up on the bridge, they're out up on a mast, they're down in the bowels of the ship, very vigorously in their imagination. So that children are still inventive, and this seems to be a very common quality. But by the time most human beings get to the graduating age from high school, they've been very greatly discouraged in their attempts to invent, and therefore they begin to lose their designing competence. The word design finally has tended, through such frustrations, into being a word that usually indicates a relatively superficial activity. Very attractive aesthetically at times. The design of the exterior of a package, the design of some decorations for a building. Designing in the sense of the industrial design. We hear that word a great deal today, and the word industrial design does represent, the phrase industrial design does represent a category in the institute disciplines, but it relates to human beings who are trained in methods of making psychologically acceptable presentations. And so the industrial designer doesn't have anything to do with electronics, doesn't have anything to do with the electronics of a telephone or the electrical circuitry and a flat iron. But he is asked to try to make that flat iron a little more attractive to the buyer. They are sort of a sales appeal, superficiality occupation. And I'm not even mildly interested in that phase of design, and I'm tremendously excited by the very large aspects of design, and not only the kind of design which these advertisers I spoke about are concerned with, that is trying to find a man who is capable and disciplined in sufficient depth in a number of scientific directions to be able to interview specialists who go in very great depth. He's able to understand what the specialist in great depth is saying and understand the significance. He's a liaison man with a man who goes in very great depth in specialization, and yet still saves himself enough of his total capital, time investment and comprehending investment to be able to understand a number of fields, and he's able then to integrate this significance and then convert this potential into tools. I'm interested in going beyond that as design. I'm interested in the design of not only the corporations which hire these designers, but I'm interested in something we get talking about in an even larger way. We talk about systems today. There are weaponry systems. There are weaponry systems that are, we say, the ground-to-air missiles systems, or we get into much larger ones. We begin to talk about the whole system of projectiles. We talk in an even bigger way. We can talk about the defense system of the country, and this would involve all the design of all the corporations and the design of the way we even educate human beings.
Fuller's Dymaxion theory of a living facility designed to meet almost every requirement through the most efficient use of all invested energy has met big challenges. In 1955, he produced the radome in answer to Air Force specifications. For use on the frozen tundra of the Dew Line, the 3,000-mile strip of radar installations on the northern rim of Alaska and Canada, the structures had to be flown to a site and set up in a 20-hour margin of predictable good weather. When completed, the installation was required to withstand 210-mile-per-hour winds, and it had to be fabricated from materials which would be invisible to the radar's microwave beam. Fuller's domes were fiberglass plastic, 55 feet in diameter. Instead of the required 20 hours for assembly, they were constructed in 14. In 1961, during a flood emergency in Puerto Rico, 100 units served as temporary housing. Made of wet-strength compression cardboard, and with the instructions for assembly printed on the material, the dwellings were put up in a matter of hours. Fuller feels the same method of instant housing could be used to alleviate many of the world's housing shortages. The first industrial breakthrough in geodesic structuring came in 1953, when the Ford Motor Company commissioned a dome to cover their rotunda. A conventional steel dome would have weighed 160 tons, much more than the building could support. Fuller's structure, 93 feet in diameter, weighed only 8.5 tons. Made of aluminum trusses with a final plastic skin covering, it carried out the Dymaxion principle of doing more with less. While weight was the challenge of the Ford rotunda, size was the opponent with the Union Tank Car Dome at Baton Rouge, Louisiana. This geodesic roundhouse has a total span of 384 feet and rises to 128 feet at the center. 23 times the volumetric size of St. Peter's in Rome, it is the largest clear span enclosure in the world. The relation of dimensions to weight and to cost shows the great economy of the Dymaxion principles. In simple units, there are 2 ounces of structural weight for every cubic foot, and the total cost of the roundhouse was less than $10 per square foot, about half the cost of a conventional building the same size. The United States Information Agency dome, used at the 1956 International Trade Fair at Kabul, Afghanistan, set a record for engineering planning, manufacture, and construction. 7 days after the contract was signed, all designs were completed. Within a month, the entire dome was manufactured and ready for air shipment. Directed only by one geodesic engineer, local Kabul laborers fastened the red and blue color-coded struts together. 48 hours after the arrival of the shipment, the dome was completed. These structures answered seemingly impossible demands, and the answers came from Fuller's conviction that beneath apparently diverse natural phenomena lies a basic coordinate system, and that by applying that system to design problems, strikingly simple solutions can be found. To describe that coordinate system, he evolved his synergetic energetic geometry, a mathematics which accommodates the requirements of many physical laws. This system gave him the mathematical basis for geodesic construction. Scientists exploring other fields have found similar patterning. Dr. Donald Casper, at the Children's Cancer Research Foundation in Boston, has constructed a model of the protein molecules in an icosahedron virus. A microscopic photograph of tissue from the human eyeball produces again the familiar pattern. Algae, photographed at the Max Planck Institute in Berlin, repeats it. In inorganic science, mathematical crystallographer Arthur L. Loeb has constructed models of the crystal structure of corundum, the basic component of sapphire and ruby, and of cuprite, a copper mineral. These examples of synergetic, energetic patterning appear in very different kinds of natural phenomena. They are consciously articulated by Fuller in his geodesic structures. But more important to him than such practical application is the underlying process of design.
So design then seems to me to be a highly objective conscious, reconsiderate, an imagination that uses a great number of experiences and integrates the effect of those experiences and discovers principles that operate in the special cases and use those generalized principles, and then is not just subjective about them, not just a philosopher about them, but begins to actually apply them and those generalized principles to many specialized cases. I find that design also then goes into a number of tools. All of these designs are realized in external actions outside of man, and they relate to man reorganizing his environment and reorganizing environment so his environment begins to work for him. So the spider can go to sleep and the net keeps on working, catching the flies, not only which are going to support her, but her regenerative function of producing more spiders. And so that these tools then get to be an extension of the internal functions of the living species, in which their function goes on even whether they're present or not. This is an extraversion of internal functions of the individual. It seems to me then to be a very, very powerful kind of a capability.
Buckminster Fuller has himself externalized the internal functions of the individual. Each of Fuller's designs is a result of years of conscious research and application of that research. The years of teaching young designers to examine and perfect geodesic structures were conscious efforts to expand the knowledge of the design scientist. For Fuller, a natural function of man is to think, and to use the results of that thought accumulatively. In the classroom, in laboratories, on construction sites, Buckminster Fuller has extended the view of the designer and of the future of design science.
I see that the design function can go in several important directions. It can go in defensive directions, to build a wall around us to protect us, where we do not do too much thinking, but we simply learn by experience a certain amount of bulk, a certain amount of physical matter will frustrate anybody trying to approach us. We can have then defensive design. This tends to be contractive, to contract the dimensions of our lives. Then there are expansive ones, designs which increase our freedoms, designs which give us levers, designs which use a lever in a multiple plurality of levers as fulcrums to make a series of pole vaultings, and that would be finally becomes the wheel with its many spokes, and that wheel then begins to increase the areas which we can visit, so that this would be a kind of design, an affirmative design, and an expansive design, where man begins to increase the totality of the area which he experiences, and he increases the amount of time of his experiences by accelerating experiences. He can have the equivalent of the experiences of many lives all in one life by an acceleration and a reorganization of the experiences, so that he can have the experiences of many men. All of that is by conscious design. We can see then how man could develop designs for keeping other men from bothering him by building a prison. This would be a constrictive design, and then he could design ways of helping human beings, as for instance he notices that a great many automobile accidents, and in the early days of the automobile accidents we used to put up more and more signs warning people that there's a dangerous area. We sent out more motorcycle policemen, had more traffic policemen. I saw that instead of trying to reform man, you could reform the environment. We could go in for divided highways. We could go in for split-level highways. We could go in for appropriately banked turns, so that people would not have any They could get from here to there with great ease. They could be themselves, and they would do logical things in relation to their natural physical senses, and would be able to get from here to there much more rapidly. So that would be what I would call, such highway design would be what I would call affirmative and degrees of freedom increasing design, in contradistinction to the stoplight, the sign which says slow down, don't get there as fast, don't have as much life, and then the very constrictive design of a prison, which you say you're a dangerous driver, and you've been a dangerous driver for so long that I'm going to restrict you by taking away your car, take away your motion. I'm going to restrict you even more by saying you can only move around within 1 acre here inside the prison. So we see that design can, consciously understood, be used to very greatly enhance our species, and it can be very fearfully used to constrict our freedoms, and if not used at all, can render us less effective than other species. I would say that what really distinguishes man from all the other living species is the magnitude to which he has employed the design capability.
The Fuller World is produced for National Educational Television by WGBH-TV, Boston.
This is NET, National Educational Television.